Okay, am I on? Tonight will be interesting. My wife decided to do spring cleaning this week, and apparently the house needed it, judging from the amount of dust I breathe. But anyway, welcome back to the fifth class of a reasonable answer for the hope that we have. And tonight we're going to look at the second part of Genesis, the lesson on Genesis. I want to review last week's lesson a little bit before we begin. And the first part of it was really about the incomprehensibility of the cosmos that God created. Scripture says simply that God made two great lights, the greater to govern the day and the lesser to govern the night, and He also made stars. And out of that simple statement we get an awful lot. I reminded you that in chapter 22 of Genesis, when Abraham had offered up Isaac as a sacrifice in obedience to God, God came and blessed him. And part of that he said in 17, I will bless you and make your descendants as numerous as the stars of the sky and the sands on the seashore. And I mentioned last week what a ridiculous comparison that is on the surface. Down through history, people have tried to count the stars, and people with good eyes can count around 2,000. The grains of sand on the seashore are countless. So keep that in mind as we go through. I want to look at the immensity, and so we start with a comparison of the sun with other stars, and you'll see immediately that our sun is really nothing to write home about. It's on the left, you have Arcturus on the right. The next picture, we have Arcturus in the front row down there with the arrow above it, and we go all the way up to Antares, which is so immense that if it were placed where our sun is at the center of our sun, it would engulf the orbits of Mercury, Venus, Earth, and Mars. Unimaginably big star. And then we had to think really big. I had to explain what a light year was. It's 6 million miles, but in terms of things we might be able to relate to, light can go around the Earth 7.5 times in 1 second. That trip to the sun that would take 106 years traveling at a steady 100 miles an hour, light makes in about 8 seconds. So the distance that light travels in a whole year is really beyond our comprehension. We looked at how they measure these things, and I introduced you to the concept of a parsec. You measure distances by triangulation. That's the way our eyes work. We get the largest base possible, the orbit of the Earth. We measure a very small angle, 1/3,600th of a degree, and that distance is 1 parsec, which is 3.3 light years or 19 million miles, a parsec. And that measurement is only good out to about 100 parsecs. Beyond that, we have to resort to a Doppler shift of the light. Everybody's, I think, experienced Doppler shifts in sound when a car goes by, and the pitch shifts from high as it approaches you to a lower pitch as it passes by. Sound does the same thing. It pitches from high blue down to red as it passes. And since everything is moving away from us, the universe is expanding, everything has a blue shift, and the faster it's going, a red shift, and the faster it's going, the more red it is. And it's observed that the faster stars are further away, and so they use this to estimate distance. Looked at a galaxy. This is a spiral galaxy. A typical galaxy like this is 100,000 light years across. Remember, distance to the sun covered in 8 seconds. 100,000 years to go across this at the speed of light. Has a population of about 100 billion stars. This is a galaxy like ours, and we would be located in one of the arms way away from the center, which is a nice place to be. This is just to remind you that they're beautiful. And we look at the violence of the universe. This is beautiful, but it's what's left of a star that exploded. It's nebula. Two colliding galaxies, and when you think of this, it's hard to get your arms around it. Here are two bodies, each on the order of 100,000 light years in diameter, each having on the order of 100 billion stars, and they're colliding. And we sing about the rolling thunder when we talk about God. And then we looked at this picture, which is taken of some galaxies located 2.2 billion light years from us. 2.2 billion light years. So it's estimated that they're on the order of 100 billion galaxies, and each galaxy has about 100 billion stars. So that's a lot of stars. Maybe Moses wasn't too far off when he compared the stars to the sands on the seashore. Out of all this, I want you to remember that by definition, whatever created it has to be greater than the cosmos. The Creator is always greater than the creation. So the power of God is greater than this. The wisdom of God is wiser than the wisdom in nature. How did it come to be? There are three possibilities. The first one, that it always existed, has been ruled out by the data that's been obtained from science. So we agree that there was a beginning, and so that leaves two possibilities. The universe is not eternal. In the beginning, it created itself from nothing. Or the universe is not eternal. In the beginning, it was created by something or someone. That's the only other two possibilities. And you need to remember that when you look at Nobie and some of these things. In the beginning, the Bible says, God created the heavens and the earth, and we looked at what that meant, and basically it says, in the beginning of time, God created the substance of the heavens and earth. In other words, He created space, He created time, He created matter and energy. And from these, in the rest of the chapter of Genesis, He's going to make things like we see them. Now, the Big Bang is the scientific explanation for this. And it proposes that the universe began with a single immense explosion from which all matter and energy originated. And the thing that exploded was about the size of a basketball. Now, if you have trouble imagining things, imagine a basketball exploding and becoming those billions upon billions of stars that we just looked at. Some thousands of times bigger than our sun. And out of that chaos comes the order as we see it. And by the way, it ignores the problem of how you get something from nothing. The Big Bang does not explain where the basketball came from. In fact, the Bible is somewhat unique in that aspect. Very hardly anything ever tries to explain how it began. They explain how it evolved, including other religions. So physics is violated, and I wanted to make the point that it's violated by either explanation. If you explain it by the Big Bang, it's violated because you get order and complexity out of chaos and disorder. If God created it, you have the laws violated because, again, you started with something and you ended up with something that's very complex and orderly. I believe that God created the laws of nature, and therefore they were not violated at that point. The Big Bang Theory does not avoid this dilemma. Okay, if the world's finest minds can unravel only with difficulty the deeper workings of nature, how could it be supposed that these workings are merely a mindless accident, a product of blind chance? Paul Davies is a world-renowned scientist, professor at Southern Cal, I think. Sir Fred Hoyle, a world-renowned astronomer, says a common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics as well as with chemistry and biology, and that there are no blind forces in nature worth talking about. So tonight I want to look at Genesis 1 and the special nature of planet Earth. We'll come back down to Earth, so to speak. First I want to look at our sister planets of the solar system. In To get a scale here, we'll look at, again, remember the sun. And the sun was 1 pixel in that picture of Arcturus, that huge star. But here's the sun compared to the planets. You have Jupiter on the left and Pluto on the right, and there's Earth, 4 up from Pluto. Sun's big. And this is the planets compared to each other. And the last one's called the terrestrial planets. The 4 big ones there are basically gas balls. And these are the so-called terrestrial planets, which have rock and hard surfaces. So you see Earth and Venus is about the same size of Earth, and Mars is quite a bit smaller. And Pluto, actually this year, I think, was demoted from the status of a planet. So let's look at Mercury. Here's a picture of Mercury crossing across the sun, orbiting between us and the sun. As you can see, it's very close, 36 million miles. Now we're 93 million miles. And the thing about Mercury is that it rotates once every 53 days, I think, 59 days. And so it's one side is facing the sun quite a long time. As a result, the side facing the sun becomes very, very hot. I want you to notice in this picture, though, that there is a sharp cutoff between the surface and space. It just turns black all of a sudden. It's obvious that there is no atmosphere on Mercury. And as a result of that, it looks a lot like our moon because it's not protected from meteorites. The temperature in the daytime, because it rotates so slowly and that one side is facing the sun so long and it's so close, is 950 degrees Fahrenheit. Now, to give you an idea how hot that is, lead melts at 621 degrees Fahrenheit. The mercury in your thermometer boils at about 273 or so degrees Fahrenheit, 673. This is 950. So there's no hard lead on the surface of Mercury. It'd all be liquid. Mercury would all be a vapor. Nighttime temperature on the night side, which correspondingly is facing away from the sun for a very long time, and since there's obviously no water on this surface and no atmosphere to scatter heat and light, the nighttime gets very cold. Minus 346 degrees Fahrenheit. Now, if you go to the Antarctic and you stay down there like, I think it was Admiral Byrd, no, it wasn't. Who was it? Went to the Antarctic. Anyway, he recorded temperatures of like minus 85 degrees Fahrenheit, minus 85 at the South Pole, which is somewhat colder than the North Pole. So this is more than 3 times colder than the coldest place on Earth, on the night side of Mercury. It's one of the coldest places in the solar system, amazingly, so close to the sun. Let's go to Venus. Venus is a much nicer looking planet. You might think about moving there. That picture up in the top is a little bit of a misnomer. It's a false color to show the clouds a little better, but don't be misled. Those clouds consist of little droplets of sulfuric acid. The atmosphere of Venus is 97% carbon dioxide. So it's a runaway greenhouse. This is what Venus looks like with the atmosphere stripped away. If we look at the surface of Venus, we see a lot of volcanic eruptions and lava flows, and it's very hot. Venus is almost twice the distance from the sun as Mercury. It's about 63 million miles. But it traps the heat that comes to Venus. It's a greenhouse, very effective greenhouse, 97% carbon dioxide. And so Venus is uniformly, front and back, sun side and night side, 900 degrees Fahrenheit. Now this is still above the melting point of lead and the boiling point of mercury. It's very, very hot. And you've got sulfuric acid clouds. You've got an atmosphere that's 15 times as dense as our atmosphere, has 225 mile an hour winds blowing continuously, and it's hot. If you wanted to think of a place that might be like hell, this would be a good candidate. Don't think you want to live on Venus. Look at Mars. This is an interesting planet. You remember back in the, I don't, it was before my time, but there was when radio first came out, one of the first shows on radio was Orson Welles' War of the Worlds, about the invasion of the Earth by Martians. And back then, some astronomers had seen in their telescopes what they thought were canals on Mars. And Mars changes colors a little bit with times of the year because it has polar caps, and they build and they recede with summer and winter. And so their color changes on Mars, and they thought they saw these canals. And so everybody thought if we have some cousins in the universe, they surely will be on Mars. And it was believed so strongly that when War of the Worlds came out on radio, some people apparently didn't hear the introduction saying it was a play, and they jumped out of buildings, committed suicide. So there was great anticipation about Mars, not just back then, but back in the 70s when we first sent probes to Mars. We sent them there because we expected to find life. By the way, let me ask you, what is the main reason for the space program, other than the fact that Kennedy wanted to demonstrate technology in the Cold War for political purposes? But in addition to that, what was the purpose of going in space? To look for life. And they've been trying ever since. It's been disappointing. Here's a picture of Mars' surface. You notice there are no lakes, no beaches, no trees, no flowers, no birds flying in the air. At high noon, at the equator on Mars, in summertime, it might get up to minus 21 degrees. Now Mars is 1.5 times as far from the sun as we are. It's about 140 million miles. The minimum temperature gets down almost to minus 200 degrees Fahrenheit. The atmosphere is about the same thickness as our atmosphere would be if you went up to about 50 miles altitude. It's very thin. And in addition to being thin, and of course it would be very difficult to breathe at that altitude, it's all carbon dioxide, virtually all carbon dioxide. A little bit of water vapor, no free oxygen. And of course, no liquid water. Now, there's a lot of talk about water on Mars, and it's apparent that one time in the past there may have been water because there are places that look like riverbeds, but there's no water today. If there is any water on the planet, it's subterranean. It's not on the surface. If it comes to the surface, it evaporates. So Mars is not promising, in spite of what people had hoped. A friend of mine out at NASA got some meteorites from the Antarctic, and the composition of the meteorite is similar to the composition of Martian rocks. So the idea is that these meteorites were at one time blown off of Mars by an impact, and they drifted around space, and they finally came and were pulled down to Earth. And in these meteorites, they have found some interesting little structures, microscopic structures. And they're all excited about maybe that was life. But when it comes down to the final analysis, you can get interesting structures from chemical reactions, the building of crystals, for example. They have found no structure that resembles a cell or a virus or anything else. So, as I say, the results here were in great anticipation, very great disappointment as far as finding life. This is Jupiter. Jupiter is basically a huge ball of hydrogen gas with some helium mixed in. It rotates every 10 hours, very, very fast rotation for something this big. Makes it kind of oval, squishes it down on its poles and spreads it out at the equator. It has a lot of storms. You see one here, it's called the giant red spot. It's been there for well over 100 years, It's bigger than the Earth. So imagine a hurricane larger than Earth. At the cloud tops, things are not too bad on Jupiter. It's very cold, minus something on the order of 170 degrees, but the pressure is about like our atmosphere. But as you go down, the pressure becomes immense, enormous, crushing. And the temperature goes to something like 50,000 degrees Fahrenheit. You see, Jupiter almost became a star. It emits more energy than it receives from the sun. It just didn't quite get ignited. The next planet out would be Saturn, which I haven't shown a picture of, but Saturn is basically like Jupiter. It's just a little bit smaller, and it has visible rings. Jupiter has some rings, but they're not visible. This is Uranus. Uranus has a small ring, but again, it's a lot like the other two. It's a gaseous planet. Interesting thing about Uranus is it does have an ocean. 5,000 miles below the cloud tops is a 6,000 mile deep ocean. It's scalding hot, and it's ammonia. Now, no hard surfaces on any of these planets. Below the ocean is a core about the size of Earth. It's radioactive. And the ocean is heated from the radiation from the core, not from the sun. Once you get out beyond Mars, satellites can't use solar arrays very effectively because the sun becomes so dim. So this doesn't receive much energy from the sun, but it does from its radioactive core. Then you have Neptune and Pluto. And Pluto is just a ball of ice, not water ice, but methane ice, which means it's below minus 300 degrees Fahrenheit in the summertime. In the summertime, a little bit of the ice vaporizes and forms a very thin atmosphere. In the wintertime, the atmosphere freezes solid. So when you think about this, I want you to now think about Earth. And here's our nearest neighbor, the moon, and you see what's required there, about 300 pounds of protection to get out on the surface of the moon. And by the way, that wouldn't be any good if there was a solar flare. It would scorch him. Fortunately, when we visited the moon, there were no eruptions on the sun. So the uniqueness of planet Earth compared to the other planets. And I think you'll see that Earth is different in kind, not just in degree. It sticks out like a sore thumb. It's obvious that something has gone on here. I don't care if you believe in God or not. If you look at what the space program has found, the data, it's obvious to everybody that something's gone on at this planet that didn't go on at any of the other planets. First of all, our sun was placed in a very good spot. It's placed 30,000 light years away from the center of our galaxy. That's important because if we were at the center, there would be so much radiation. There would be black holes sucking matter in, too much going on, and it was to be too unstable, we'd never survive. But we're way out, 30,000 light years, on an arm, one of those little spiral arms, and a little cul-de-sac that's quiet and nothing much going on. We were placed just right. Scripture says, now the earth was formless and empty. Darkness was over the surface of the deep, and the Spirit of God was hovering above the waters, or over the waters. Do you ever wonder what the Spirit was doing hovering there? Was he just, hovering, or was... Well, it was formless, it says. So let's look at some things about Earth that make it possible for us to be here tonight, without which we wouldn't. This is a picture of the surface of the sun that I showed you last week. And you can see that there's an awful lot going on the sun. It's extremely hot. It blows out million-degree gas that travels out through the solar system called the solar wind. It emits all kinds of radiation, ultraviolet radiation. It emits cosmic rays that are million or billion electron volt energies, all kinds of bad stuff, a lot worse than what gives you a sunburn. And we're exposed to that. Our Earth is. So what happens about it? Well, the Earth, as you know, has a magnetic field. And this is kind of a simplistic look at it, but it's kind of like a bar magnet with a north and south pole. And the field lines extend out into space around the Earth, okay? Now, if we place this in the solar wind that's being blown off of the sun at 300 to 700 kilometers per second, very fast. A kilometer is about 0.6 of a mile. This wind, which is ionized, there are electrons and ions, not neutral atoms, but protons and electrons. They come off and they smash into this magnetic field. And they're not able to cross field lines. You'll have to believe me there. Physics says that charged particles can't cross field lines. They get trapped on field lines, they spiral around them. So you'll see the field on the left is smashed down a little bit toward the Earth. And also the field on the right, downstream, is pulled out, stretched out. And it stretches out into what's called a magnetotail. This whole thing is called a magnetosphere. And it surrounds the Earth like this. This is what it would look like if you could see it. You can't see it, it's invisible, of course, but there's a bow shock. The first thing the particles from the sun run into is a bow shock, and that slows them down. And then you have the Earth's magnetic field, and you have this front lobe that's mashed down and the back lobe that's pulled out and stretched out. Down in close to the Earth, you have the Van Allen radiation belts, and the magnetic field is then separated into two groups, closed field lines, which start at the North Pole and come around and connect to the South Pole, and open field lines that go out into space for hundreds of thousands of miles. In fact, the magnetotail is so long that the moon at certain times passes through the Earth's magnetotail. Now, why am I telling you this? Well, this is how we get rid of cosmic rays. The charged particles are diverted around the Earth by this structure that you may not have even known was there. Without that structure, life could not exist on this Earth. So next time you use a compass, think about it. It does a lot more for you than just find your way. Let's see, can I go back? I did that too quick. Okay, there were holes, you noticed, in the top and the bottom. And those holes allow, there's two places on Earth that particles can come in. They're called the, can you go back to? There we go. They're called the polar cusp, you see up there. Those little funnels, particles can come down, energetic particles. Everywhere on Earth we're shielded from it except those places. And those particles, when they hit the atmosphere, this is a picture from above the atmosphere taken from the shuttle, you see these streamers. These are very energetic electrons, and when they hit the neutral atmosphere, they excite it, and the atmosphere emits light. And that's what you see. And of course, that's the way the aurora borealis is formed. That's what it looks like from the ground. Okay. The scripture says, and God said, let there be an expanse between the waters to separate the water from the water. So God made the expanse and separated the waters under the expanse from the waters above it, and it was so, and God called the expanse sky. Now, why is that important in this context? Well, you know, we looked at Mercury. It has no atmosphere, and it's all pocked up. Here's the moon. The sun's coming out from behind the moon, and you have three planets there, Mars, Saturn, and Mercury. Mercury being closest to the sun. And it's clear there's no atmosphere. You can see the sun shining right around the edge of the moon there. And the moon is all pocked up. It has no atmosphere, has no cushioning effect when it's hit by meteors. The Earth has an atmosphere, as you see on the bottom of this slide here, taken from orbit around Earth, and that's the moon up there. And the Earth's atmosphere extends about the limb, the part where you can see it, the visible atmosphere, extends out about 60 miles from the surface of the Earth. Has a density, exerts a pressure at sea level of 15 pounds per square inch. And what that does, of course, is it burns up. As particles come in, starting at about 100 miles up, before you can actually see the atmosphere, before it's visible, they begin hitting so many particles, and the resistance gets so high and they get hot. How'd that happen? that they burn up. This thing works great when it's pointing at the ground. How many does that? Okay. So they burn up. 10 metric tons of dust fall on the earth every day from burned up meteorites. It's a very effective shield, and that's why we don't have craters everywhere. We have a few, but not many. Okay, the ozone layer. You've always heard of the ozone layer, and everybody's worried about holes in the ozone layer. It's a layer that exists actually from about 20 miles to about 60 miles. The 40 miles is probably the peak of it. Ozone, the oxygen you breathe is O2. It's 2 atoms of oxygen bound together to make an oxygen molecule. The ozone molecule has 3 oxygen atoms, and it's entirely different. It's what you smell if there's an arc or maybe an electric motor running. It has a peculiar smell. But it also has an interesting characteristic. It's a very effective absorber of ultraviolet radiation. And so it absorbs the radiation. There we go. And this is what happens to the ultraviolet. There's 3 types, UVA, B, and C. C is the bad guy. It's the one that causes cancer. The others cause sunburn and various things, but the CU is the most energetic and the most harmful. And on the left, you see altitude, 20 kilometers, 40 kilometers, and 60 kilometers. And the orange or yellow curve there is the density of ozone. So it peaks out, in this case, about 20 kilometers. And you can see the absorption of UV. Most effectively, it absorbs UVC, which is the worst and what we need to get rid of most. UVB, a little bit gets to the ground, and UVA, quite a bit gets to the ground. Your glasses, dark glasses when you buy them, will be to filter UVA and B usually. Some of them just A. So we get rid of ultraviolet. Now let's look at the chemical characteristics of our atmosphere, and you know that it has oxygen, and you notice that no other planet in our solar system has free oxygen in the atmosphere. It has 21% oxygen, 78% nitrogen, and you think, well, why is that? It'd be better if we had more oxygen, wouldn't it? Well, not really. If we had 100% oxygen, everything would burn up. Have you ever done the experiment in science lab when you take a match and you blow it out and you stick it into a test tube of oxygen and it almost explodes? Forest fires would never go out. Our metabolism would go wild and would probably burn up. See, the nitrogen moderates oxidation. Nitrogen is an inert gas. It doesn't interact. And so when oxygen combines with things that have carbon in them, like wood and flesh and paper, the nitrogen's there and it keeps it from progressing too fast. So if it weren't 78% nitrogen, we would have a problem. And carbon dioxide, I threw that up there. There's some other minor things, but I just wanted to show you this. Remember that Venus was an example of a runaway greenhouse effect. 97% carbon dioxide. On Earth, we have 0.03% of carbon dioxide. It's not enough to do anything. And all deference to Mr. Gore, we don't have a greenhouse effect yet. Now, if we keep on burning stuff for another 1,000 years, it may come to a point where we do. But today, the greenhouse effect is not causing our Earth to warm up. Earth's oceans. I want to begin with Scripture says God made 2 great lights, the greater light to govern the day and the lesser to govern the night, and God set them in the expanse of the sky to give light on the earth and to govern the day. He set them. And I want you to think about this, why we have oceans. Just because we have water, we wouldn't necessarily have oceans. Here is what's called the water band. Most stars, all stars, I guess, have a water band, a certain distance from the star where the temperature would be right to have liquid water. If you're closer than this band, then the water would evaporate. It'd be too hot. And if you're further away, all the water would freeze into solid ice, and you wouldn't have any liquid, and you wouldn't have life. So Earth just so happens to be placed in this water band for the sun. It extends about 5% closer to the sun than we are and about 50% further away. Now, there are other things involved in having oceans, like cloud cover, the greenhouse effect, heat that comes from the radioactive core of the planet, and other things like that. All these things have to balance out for us to have oceans, but starting with our position, our distance from the sun. If the sun were to brighten 10%, it would totally evaporate our oceans. 10%. Now, there are all kinds of cycles that the sun goes through. The most prominent one is a 13-year cycle, but it gets brighter and dimmer. It gets more active, more solar flares and prominences and black and holes in it. But 10% brightening would do us in. Now, it turns out that right now we're in a phase where the sun is becoming brighter. That's why it's getting warmer. And in fact, several scientists admitted this last year, right before Mr. Gore had his world tour of, what was it, they played music and whatever, to make people aware of the greenhouse effect. Science now recognizes that it's not the greenhouse effect that's warming the earth, it's the sun, which is the most important input to our weather. We could do away with all carbon dioxide in the atmosphere and it wouldn't change the temperature of Earth. The sun's controlling it right now. So, as a result of where we're placed and all is balanced, 71% of the Earth's surface is water, oceans. Then it says, God said, let the water under the sky be gathered into one place and let the dry land appear. And he called the ground land, the dry ground land, and the waters he called seas. And that's indeed what we have. There's South America, and there are the oceans, the Pacific and the Atlantic. And we look at scenes like this and we kind of take it for granted. But it wouldn't occur anywhere else that we know of in the universe. Let's look at the plant life and animal life. God said, let the land produce vegetation, seed-bearing plants and trees, and the land that bear, I think that's trees on the land that bear fruit and with seed in it. And so we see all kinds of vegetation on the earth, plants with seeds and what have you. And God said, let the water teem with living creatures, let the birds fly above the earth across the expanse of the sky. He said, let the land produce living creatures. And so we see birds and we see living creatures of all types. And they're all interdependent, aren't they? The creatures depend on the plant life. Fish depend on there being oceans. And then we come to mankind. And God said, let us make man in our image. We talked a little bit about what that might mean a couple of nights ago. Oops, I went too far. Can you go back one? Okay. And he said, be fruitful, increase in number, and fill the earth and subdue it. And I would submit to you that's the one command that we have obeyed. We have subdued the earth and we have filled it. There are a lot of people on this earth. Again, can you imagine seeing that scene on Mars or Venus? On Mars, there would be no water. It would be frozen if it were there. On Venus, there would be no water. It would be evaporated, 900 degrees. I want you to think of something now that you may think is a little bit silly. The uniqueness of water. When it freezes, it floats. Now, things don't have to be complicated to be important. The fact that ice floats, you've all seen that if you drink iced tea. Why is that important? By the way, it's about the only thing we know that does that. Liquid, solid iron doesn't float on liquid iron. Hardly any other element or combination floats on its liquid phase when it's solid. Water is unique. As it gets colder, it begins to contract like it's supposed to, and then at 4 degrees centigrade, where it freezes at 0, as it gets to 4 degrees, it starts expanding from there up to 0. And it expands 10%, and that makes it float. Now, why are we concerned about that? So we can have iced tea and our ice can stay on top of the glass instead of sinking to the bottom? Think about what would happen if water didn't behave that way, if ice didn't float. Suppose every winter, and by the way, just to give you an idea, there's some icebergs, and remember that 9/10 of that is below the surface. That's the 1/10 above. And this is what the Arctic looks like. But suppose every winter, when the ice froze, it sank to the bottom of the ocean. What would happen? Huh? Well, it only increased the volume by 10%, by 1/10%, by 10%. Eventually it might, but what happens in the summertime in the Arctic? The sun shines, doesn't it? What happens to the ice? It melts. Even in the Antarctic, in the summertime, you see the cleaving off of the ice shelf and all these things happening. That's where you get those icebergs. And they float down into the tropic zones and they melt. Suppose it went to the bottom of the ocean, what would happen to it? It would stay there forever. And the next winter, some more would come. And the next winter, some more, until finally the whole earth would look like that. And in the summertime, you might have a little bit of puddles on the surface, but that'd be it. There would be no oceans. We'd virtually have no water if ice didn't float. And all these little things that just so happen, that God put here that we depend on. And some of them we don't even know about. Paths in the ocean. There's a man named Matthew Fontaine Murray. Have you ever heard of him? It's an interesting story. Matthew Fontaine Murray was sick one time, and on his sick bed, his grandson came in, the story goes, and some people say it was his wife, but anyway, one of them came in and he asked him to read the Bible to him. And they were reading through this passage in Psalms 8, verse 8, and it said, "And the birds of the air and the fish of the sea, all that swim in the paths of the seas." And Matthew Murray said, "Read that again." And then he said, "If they're paths, God says they're paths in the seas, they're there, and I'm going to find them." So he went out and he found paths in the seas. Now, what do you think that means? For roughly, I guess, 100 years at least, the British would come over here, and they would get almost here, and they would spend weeks and weeks making it the rest of the way, because they ran into the Gulf Stream, which was flowing against them. And some American captains told them, if they'd just go over a few miles, they'd be out of it. The British were too proud, and they sat there in the Gulf Stream making a knot or two a day. Matthew Murray found the paths in the seas, the streams of water. And then another one he was interested in, Ecclesiastes 1:6 says, "The wind blows to the south and turns to the north, round and round it goes, ever returning on its course." Matthew Murray took these things literally. A few years ago, we had a science meeting in Annapolis, and I had read about this, and I'm always a little bit skeptical, so we were meeting about a block out of off the campus. And during lunch one day, I walked onto the campus and I went to the visitor center and asked them if they had heard of Matthew Murray, because supposedly there's a statue or a something there anyway commemorating Matthew Murray, and I mistakenly called him Matthew Fontaine. Well, after I got back a week or two later, I got a letter and they said, "Oh yes, that's Matthew Fontaine Murray," and yes, there's a commemoration to him. In fact, it quotes the Psalms 8, verse 8 on it. And he is indeed considered the father of modern navigation. This is what's written on a monument at Goshen Pass, Virginia. He was a Virginian, and the state of Virginia did this in honor of him after he died. Matthew Murray, Fontaine Murray, pathfinder of the seas, the genius who first snatched from the sea and the atmosphere the secret of their laws. This is what he found. The Gulf Stream is you can see the United States, and the Gulf Stream comes out of the Gulf of Mexico and into the Atlantic, goes across almost to England, and then on up into the Arctic Circle. That's why it's not so cold in England. If you look at the map, England is even with Nova Scotia or Maine. Yet you go over there and it's usually not very cold, hardly ever snows because of the Gulf Stream. Stockholm, Sweden has less extreme weather than we used to here in Huntsville. It used to get down to below zero here, and it hardly ever goes below zero in Stockholm. It stays cold longer, but not as cold. So these are important things, and they tremendously influence navigation. It saved people tens and tens of millions of dollars, and I could go on about Matthew Murray. But anyway, here's some of the things he did. Pathfinder of the seas, mapped the world's major ocean currents, mapped the world's major wind systems, father of modern navigation, and he initiated the science of oceanography. All because he took God at his word. I want to finish by talking about the incomprehensible love of God. We've looked at his creation and how incomprehensible it is. How about his love? In the beginning, John says in 1:1, was the Word, and the Word was with God, and the Word was God. Through him all things were made. This Word, which we'll find is Jesus, made everything in the cosmos, everything that we've seen. The Word became flesh and has made his dwelling place among us, and we have seen his glory. Now that is really hard to get your arms around. Something great enough to create the cosmos came to this earth, which circling around this little sun that's less than a pixel in the picture of some of the other stars. And all this vast thing, he came here and became one of us. He was in the world, and though the world was made through him, the world did not recognize him. He came to that which was his own, but his own did not receive him. Most amazing. Yet to all who receive him, who believe in his name, he gave the right to become children of God. For God so loved the world that he gave his one and only Son, Jesus Christ, that whoever believes in him shall not perish but have eternal life. And he goes on to say, but whoever does not believe stands condemned. To me, that's the most difficult thing to believe. I want to end tonight the way I did the other night. Paul tells us, for since the creation of the world, God's invisible qualities, his eternal power, his divine nature, which we've seen both of now, have been clearly seen, being understood from what has been made, so that men are without excuse. And again, I would suggest that we of all generations are without excuse. Next week, we'll look at Jesus the man, an inescapable historical fact. Thank you for coming, and see you next week.